Good. 5.1 and 5.2, which are actually graded, ready for you guys to see, but few people still make it up. Give me 1 or 2. But we took a quiz on 5.1, 5.2, so that should help your mind kind of establish itself. Okay. 5.1 and 5.2, that quiz we took, what were they requiring? What were we going over? What were we trying to get better in 5.1, 5.2? No.
The T-chart.
Good, the T-proofs. And the T-proofs, okay, the T-proofs, what were you given that you had to use the T-proof to show?
Trig identity.
An equation, a trig identity, good. And the trig identity had like some trig stuff on one side, maybe a number, maybe some other trig stuff on the other side. What did we do in the T-proof, or what did we try to do? Make connections with these formulas that we know, like the basics of, give me one of the basic formulas. Give me something from the quotient category. What's one of the formulas in the quotient category? Tangent of u equals sine of u over cosine of u. Okay, now give me one of the Pythagoreans. Those are important.
Sine squared u plus cosine squared u equals 1.
That's like the nice one. Sine squared u plus cosine squared u is 1. There are other ones, of course. Give me one of the basic ones from the reciprocals.
Sine of 1 over.
Good. Sine of u equals 1 over cosecant. And there are many others. Good job, Chris. You can study. And then we have, I think, like the even and odd, and we have the, what was the other one? The cofunction. But we didn't have to memorize those. Thank goodness. We tried to use those formulas to plug in to one of the sides and to change it up, right? We talked about puzzles a lot at the beginning of the semester. We talked about how like we're just trying to learn how to work the pieces. What's changing in section 5.3? Let me go back to the very beginning. What's changing in section 5.3? We have to use the unit circle, and that's actually a big, giant good job. That's a big change, I guess. That's a big change for us to realize in section 5.3. The unit circle is huge. I had you guys go like find in your notes where the unit circle was, section 4.2. Today you might want to still have a pencil or a pen or a bookmark or your finger in that section to turn back. So you need to be studying your unit circle again. Why is it so important that we realize the unit circle has come back? How many answers are there in 5.3? What'd you say? More than one. Sometimes. Usually. Usually more than one. What, Joel? It's limitless in the sense of how many. But it's limited in the sense of which ones. It's limitless in the sense of how many answers. But it's limited in the sense of which ones. Meaning, trig identities versus conditional equations. We talked about this on Friday a little bit. Trig identities versus conditional equations. I think this is the beginning of section 5.1. Let me just go back there real quick. Maybe it's 5.2. What was the difference between conditional equations and identities? Only sometimes true. So it's limited in the sense of it's not going to be the equations that we're seeing in 5.3 are not always true, not true for every single angle out there. So we need the unit circle to help us figure out which one is true for. So it's limited in the sense of which answers, but it's, Joel is right, limitless in the sense that we can have infinitely many answers. Because, let's review. This is how it's different than T-proofs. T-proofs are always true. Doesn't matter the angle. Plug in any angle you want. Cosine of any angle times secant of any angle will always equal 1. That's why those were kind of nice, even though they were tricky. You could plug in 30 degrees, it's true. Plug in 67 and 67, it's true. Plug in 11 pi over 12, 11 pi over 12, it's true. This one, only sometimes true. But Joel said it's limitless in the sense of how many answers, and I agree with him because, for instance, if I was to give you something like, I don't know, cosine of theta equals root 2 over 2. Someone tell me somewhere that's true. Good, 45 degrees. In radians, that would be pi over 4. Okay. This is one place that's true. One answer. But I didn't tell you just to solve a trig inverse. We're going back to section 5.3, which means I'm asking for more answers. How Nick said there's usually more than one. I can find it. I want to see if I did that. There we go. So I'm looking for more than just the trig inverse, more than just one answer. So where's another answer?
7 pi over 4.
7 pi over 4, which would be right below 2 pi. So not quite all 8 pieces when I cut into fourths. So I have 4, I have 5, I have 6, I have 7. Good. Cosine is positive in the first quadrant and the fourth quadrant. Someone give me another place that's true. 3 pi over 4 would be root 2 over 2. The problem is it'd be a negative. 5 pi over 4 would also be a negative.
Oh, negative.
Okay, so we could put as answers, we could put pi over 4. We could put 7 pi over 4. Someone just added negative pi over 4. How are they right? Negative pi over 4 is a different way of getting to the same place, right? Okay, give me another answer. Negative 7 pi over 4. But now I'm going to really stretch you. Give me another answer. 9 pi over 4. How many you get there? If you cut into fourths, you would have calzone number, all 4. You have all 8.
Oh.
9. What do we call 9 pi over 4? If it's pi over 4 plus 2 pi, or pi over 4 plus 8 pi over 4. What's the name of an angle that you revolve or go an extra revolution but land on the same spot? Coterminal. So 9 pi over 4 is coterminal with pi over 4. The same way negative pi over 4 is coterminal with 7 pi over 4. But instead of adding 2 pi to get to this one, what would you do instead? You would subtract 8 pi over 4 to get there. If I could subtract 8 pi over 4 from this one, I would get to that other coterminal one of negative 7 pi over 4. So question, that one has 3 different options. Let's get a third for this one. How could I get a third option for 7 pi over 4? We could subtract another 2 pi, that's true. If you want, we could subtract another 8 pi over 4. Or what did we do with this one to get the other one? We added. So what can we do to this guy? Add. And when we add 2 pi, we'd add 8 pi over 4. Wouldn't that be 15 pi over 4? So far we've gone to this one by just going straight to him. We've gone to 7 pi over 4 by going straight to him. We've gone to this guy by going the negative direction. We've gone to this guy by going the negative direction. Then we went to this guy by spinning all the way around and landing on him. We've gotten to this guy by spinning all the way around. See if I can get to him. And landing on him. Now it's just getting confusing. But mathematically, couldn't I keep on adding 2 pi, adding 2 pi, adding 2 pi, and it spins more and more and more before it lands? So how is Joel right? How are there limitless answers to this one conditional equation? You can keep doing more and more revolutions, and you can keep adding more and more multiples of 2 pi, which we would call plus 2 pi n. More and more 2 pi's. So there's limitless answers, but why is my answer also right when I say, but there are limited locations? It only works at the 45 in the first quadrant and at the 45 in the fourth quadrant. So, limited but limitless. Interesting. Limited but limitless. I wonder if there's other things in life that are like that. Limitless and yet limited. Deep question. Now, how did number 13 get a little bit trickier than the cosine of theta equals root 2 over 2 on the board? What was the extra part that we had to do before the unit circle, before the limited but limitless sort of idea? We gotta get the cosine by itself. We gotta get the trig by itself. We had to actually do some algebra and move stuff around first. So didn't we add cosine to the other side, get it by itself, and then we said, ha-ha, our fact. When is cosine negative 1/2? Oh, when is cosine negative? Oh, quadrant 2 and quadrant 3. So we're thinking unit circle. And then we had to think about, oh, it's going to happen at our, ooh, careful, not over 4. That'd be root 2 over 2. This is going to be at a 60 degree or at a over 3, right? So we figured out our 2 pi over 3 and our 4 pi over 3. And then what was this all about? It's getting our limitless answers, but limited locations, limitless answers. This is getting all of our, what was that name again for the ones where you spin and land? Coterminal. All of our coterminal angles. And what in the directions told me to do that?
Oh.
So what was different in this example? Okay, A, the directions are different. It gives us boundaries. So this is back to what Nick said earlier. Not infinitely many like Joel's, because it doesn't say all, but it says all but restricted. All but only looking at negative 180 and positive 180, or negative pi and positive pi. But hold on, that just tells me what kinds of answers. Limited, not plus 2 pi n. Only the locations within a certain interval. But the problem is we still had to get down here. What was it even a little bit harder in this example? We had to use a transforming technique from our t-proofs. We had to use the idea that, wait, can we make sine squared and cosine squared, can we put them together right now?
No.
No. If I subtracted, I couldn't put them together. They're not like terms like the last one. But, can I change it up? The answer is yeah. What property allowed me to say sine squared is equal to 1 minus cosine squared? Now, there is another way to do this problem. Because did all of you guys always solve t-proofs the same way every single time? No. And some of you, like, I kept getting stuck. But that doesn't mean that you weren't going in some sort of direction, just maybe it wasn't leading you to the right spot. And some of you didn't really know your formulas, so that wasn't helping a lot either. But mathematically, could I have divided both sides by cosine squared? Could I have divided by, and then divided by, and gotten here? Some of you might have liked this more. Can anybody see what t-proof, or I should say transforming?
Oh, that's
We could do the sine.
Oh.
Sine over cosine is tangent, so sine squared over cosine squared is. What could we have done if we had gotten tangent squared equals 3? I wonder if we would have gotten to the same place. How would we have solved for, can't get to x yet, he's stuck. How could I get tangent by itself? Square root. And the idea of the square root, its absolute value, I need a plus minus, long story short. So square root, I'm going to end up with a plus minus eventually. Any cheater chart people out there? This is where it's your time to shine. Any cheater chart people?
Oh,
And then show you too. Cut off. 3, 2, 1. No, 1, 2, 3, 3, 2, 1, all over 2. Square root of 3 over 3. 1 square root of 3. 60 degrees.
Good.
Okay, 60 degrees. This would happen at 60 degree reference angles in, why am I going to say all quadrants? Doesn't matter positive, negative. So, wait, radians, 60 degrees, aren't those all the pi over 3's?
Whoa.
Perfect. Same answer. So just like our t-proofs, is there only one way to go? No. But did we have to somehow deal with this sine squared, cosine squared not being the same?
Yes.
Yeah. Either divide and then use tangent, I should say tangent squared, or Pythagorean to then get like terms and combine and solve. So we're combining, or I shouldn't even say we're combining, we're using the skills we tried to develop in 5.1, 5.2 to make possible the problems in 5.3. And once we figured out at all the 60 degrees and all the quadrants, then we had to go back to our directions and say, but I'm only allowed to look between negative pi and pi. So I was able to go to pi over 3. That one was legal. I was able to go to 2 pi over 3. That one was legal. I got those two. But why didn't I keep going to 4 pi over 3? Remember, pi is going to be 3/3, right? I can't go to 4/3 or 5/3 or 7/3 or whatever else I want. And then same thing going the other direction. So I had to go, or I could go, and I should go negative. So that's what I did next. Then I went negative and said, oh cool, I can go negative pi over 3. Like you guys did on that one. You saw you could go negative pi over 4 and you were right. So we went negative pi over 3 in the interval, and that was good. And then we went negative 2 pi over 3. Those are the only things. Now, we were on this one on Friday. We're back to where we kind of started. But we've gotten all the background. We're in chapter 5. We're playing with these trig identities and formulas and trying to be able to use them to change things up. Section 5.3 says we're giving you this equation that's only sometimes true, and you need to figure out the times that it's sometimes true. But it's not going to be as easy as like, oh, just go look at your unit circle. It's a little harder. Have to use our skills from 5.1, 5.2. Can you remember what we did? We started here. And I asked, or you asked the question, some of you were like, why don't we distribute this? And I was like, can. Except I put something up on the board if I remember right. I think I put something like a factored quadratic, like this. And I said, but wait a minute, don't you like it when factors are equal to 0? How do we solve those? Set each one equal to 0. So what did we do when we had these factors equal to 0? We set this one equal to 0, right here. But what else do we set equal to 0? Back there. But now we need to solve. Now first of all, I haven't started writing answers for this guy at all, but I think we should be able to do it pretty quickly with unit circle. Where did I get these answers from? We had just started here when we had to stop. Why do I have pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2? Where cosine is 0. Why didn't I divide by 2 right away? It's cosine of, the 2x is stuck inside the cosine. I have to undo the cosine first. So, in order to undo the cosine, I have to think about cosine inverse, which says, look at the 0 and tell me when cosine is 0 before I can ever get to that 2x. Now I've gotten there, but I had to think about when is cosine 0. And cosine is 0 at, if you guys have your unit circle, go peek. If you're trying to remember, sine counts up. 1, 2, 3, so 0 would be at 0, 1 would be at 90. Cosine counts down, which means it's going to end at, we could think the x is 0 at 90 and negative 90. So cosine the x value is 0 at 90 and negative 90, aka pi over 2 and negative pi over 2. First of all, why am I not showing any negatives? What's my interval say? 0, 2, so only positives. So no negatives, so I have to go moving only the positive direction, which you see up here. But why did I keep going? So pi over 2, okay, totally legal. 3 pi over 2, totally legal. 5 pi over 2, I kept going, but I still had more space. I could go all the way up to 7. Wait a minute, 12. What? I don't get it. Why am I going to 12 pi over 4? What would this be in 2s? Wouldn't that be 6 pi over 2 if I cut it in halves? So why did I keep going? Am I done yet? Because we have to get who by himself. So what do I still need to do? Divide by 2. Or another way of dividing by 2, which might be easier for a lot of you guys in this problem, is to multiply by a half. Now, I'm going to be kind of weird just for a little bit. I'm going to leave this big old awkward space. I'm not done solving for x until I multiply both sides by a half. Which means, are my answers really going to be pi over 2, 3 pi over 2, 5 pi over 2? What are my answers going to be? Good. X equals pi over 4. Is that in my interval?
Yeah.
Yeah. Oh, 12 pi over 4. I think that's why I wrote that. Because I'm trying to think of which floats I can keep. Here. Okay, keep going. What's this one going to be? Is that one still good? Yeah, it's under 12 pi over 4. Keep going. 5 pi over 4. 7 pi over 4. Wait, I still have a lot more pi over 4s to go. Which means that I have to stop here.
Okay, do you guys find a pattern? Come on, some of you are pattern people. I had 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. What's the next one going to be? Is that one going to fit?
Yeah.
What's the next one going to be? Oh, I get the pattern. It's every odd, right? Wait, but what's bad right now? I am over 12, right? So you can basically just keep going until you're like, oh, nope, it's going to be too big, and I can't even write 13. This is a struggle. You would start writing 13 pi over 4 and then be like, oh, no. So stop there. My answers are that many. And just for those of you that like patterns. If we're going between 0 and 3 pi, in theory, we would have, if there are 2 different locations, we'd hit that once, twice, 3 times. We'd have 3 answers if it was just a plain old X. But what did we have instead? And so we should have twice as many answers than we do. It's silly, it's a pattern, it might help a few of you guys make sure you have enough. But the long story short is when you have what we would call a multiple angle, that's what this guy's called. A multiple angle. First of all, he's stuck inside the trig until you unit circle, until you use the inverse idea to get rid of the cosine. So he's stuck until we undo the cosine, but then we're able to cut everything in half, and when we do, we allow more answers in, because what was too big is now just fine. But there still comes a point where we have to stop and say, all right, too crazy. It says to stop at 3 pi, so we will. Now guys, those are all answers. Struggle, but what do we still have down there? This whole other possibility, like, wait, this guy could have been 0 too, that would have worked. But this one's a little bit easier. Is there any, like, crazy 2x inside? No, it's just an x. So all you need to do is get rid of the cosine, and you get rid of the cosine, go back to what Jackie said, use the unit circle. So where is cosine negative 1/10?
$60.
60 degrees. So we end up now, hold on, pause. Some of you might just be too tired, so everyone stand up real quick. Stand up. Still at the board. Let's see if we can get you guys a little more active. If everyone here do a quick high five, I know you're stretching. That's good. Ow! Get out. Okay, now look up here. I just asked you guys, when does cosine equal negative 1/2? How many quadrants? Just 2, because it's only negative. 2 quadrants, it's positive. Okay, question, when is cosine negative? Which 2 quadrants?
2 and 3.
All are positive. Not quadrant 1. Only sine is positive. Oh, so cosine is negative. Okay, so quadrant 2, that one's good, right?
Yeah.
Help me out. All, not that one. Students, oh, that one, quadrant 2. Where else? Tangent. Not cosine. So cosine's going to be good in quadrants 2 and 3. Okay, 1/2. Those of your brains that are thinking of little baby ordered pairs all the way around and thinking over a little, up a lot, you should have landed on, not 30, 60. But if your brain doesn't normally jump to the ordered pairs in certain quadrants or over a little, up a lot to get to different angles, what should you be thinking of? When I sing 1, 2, 3, what am I talking about? Sine. And when I sing 3, 2, 1, what am I thinking of? And when I say all over, what am I missing? Square root. Square root of 1 is 1. Square root of 2, don't know. Square root of 3, don't know. Square root of 3, don't know. Square root of 2, don't know. Square root of 1, I know is 1. When I sing, what's the last line?
Square root of 3 over 3, 1 square root of 3.
What am I singing?
Tangent.
So when I ask you guys, when is cosine negative 1/2? Quadrant 2, quadrant 3, 1, 2, 3, no, that's sine. 3, 2, 1. Where should we all be able to land?
degrees.
Okay, now, do we have to make the extra jump because we're in radians to say, oh, 60 degrees are what in radians? Yes, we have to make the extra jump. But pause and come back. Once we make the jump and get the pi over 3s, kiddos, just think calzones. How many calzones, if it's cut into thirds, how many calzones are one full 0 to pi?
3.
3. But I'm in the quadrants, how many pieces do I have? 3 minus 1 is?
2.
That's 2 pi over 3. If I'm in the third quadrant, it's all 3 pieces plus 1.
4.
So what are my answers? 2 pi over 3.
4 and then 4 pi over 3.
4 pi over 3.
Oh my.
But wait, what's my interval?
0 to
So to 3.
So I have 3 calzones. So I hit the 2 pi over 3. That's 1. That's between 0 and pi. I hit the 4 pi over 3. That's between 0 and 2 pi. But aren't I allowed to keep going?
Yeah.
So how do I get to that one? I have 3. I have 6. I have 9. Ooh, take
Minus
one.
1. Ooh.
8 pi over 3. So my final answers are, sit down and write, x equals. It's okay, help you track a little bit, yeah? 2 pi over 3, 4 pi over 3, and then 3, 6, 7, 8. What was another way to get to 8 pi over 3?
Yeah.
Add 2 pi to that guy, because he's coterminal. He's coterminal with the first one. I had my 2 pi over 3. I'm going around the first time. I had my 4 pi over 3 when I was able to keep going. But I knew I could get back to the second quadrant because I still had one full half turn to make to get to 3 pi. So I was like, all right, I have 2, I have 4, 6 would put me right here. 8 would get me back to the 2 pi. So what are all my answers? All of those and all of those, but pause. Does the unit circle have to be hard?
No.
No. Pick a way that works. Pick a way that works. I've been asking you since September? October? Pick a way that works. And make it work for you. But when I'm saying 1, 2, 3, 3, 2, 1, all over 2, square root of 3 over 3, 1 square root of 3, do you see what I'm thinking of?
Yeah.
Now what if I was to ask you something like, when is cosine 0, like we had a second ago? Where is that in this?
90. What? That's 90 degrees.
Because cosine starts high and ends low. What are the angles I'm missing?
0 and 90.
Sine starts
0.
low and ends
High.
high. Right?
Yeah.
And tangent says, well, what's 0 divided by 1? Because tangent sine over cosine, quotient property. We've been doing it since the cheater chart.
1.
0 over 1 is
0.
0. Ooh, what's 1 divided by 0?
Undefined.
There we go. The whole unit circle, 1 cheater chart. The song gets most of it. All right. That's number 22. We finally made it. Let's make the interval smaller. Let's make it just 0 to 2 pi. Sound good?
Yes.
No 3 pi. That's getting a little too crazy. But I need some help. I need to get x alone. But before I can do that, I need to get the trig alone. So I can undo the trig and get to x. The problem is, I got a sine and a cosecant.
I got you.
I wish they were related.
They are.
Huh.
Sine 1 over cosecant.
That's a great one. We could make sine 1 over cosecant, but then we're going to be stuck with cosecant.
Wait, don't they cancel out?
What was,
Oh, wait.
no, if it was times.
Yeah,
If
yeah,
it was
yeah.
times. The addition, okay.
So Joel was like, hey, if it's times, 1 over cosecant cancel, and that's plus.
Oh.
Do we want to be stuck with cosecant?
No, ma'am.
So let's change cosecant to be 1 over
Oh my goodness.
plus. Gotta keep it legal, no canceling out anything, it's addition. Ah, how do I add when I have a fraction and a non-fraction and the denominators don't match?
Common denominator.
Common denominator. So who needs the common denominator? Come on.
On the left.
Because he just has an over 1, yeah?
Yes.
So common denominators, I multiply top and bottom by the other guy.
Oh.
Because when I multiply top and bottom, that's just multiplying by 1. 1 doesn't mess anybody up when I'm multiplying. Anything times 1 is himself, just in this case, it'll look a little different. He's been transformed.
What's that one car's name? Is it Bumblebee? The yellow, is it a
Yeah.
Corvette? Right? Is it a Corvette or Camaro?
It's a Camaro.
Struggle. Okay, I know guys, I know.
What's
The yellow Camaro, is that Bumblebee?
Yes.
It's a big old monster Bumblebee.
Yeah.
It's the same guy, so when I multiply by, no change how he looks, but same things, right? Okay.
Where's Megatron?
Okay, so we have 2 sine squared. Yes, I'm trying to keep you guys awake because you're all like, when you walked in. All over sine. Do you guys agree?
Yes.
How do I keep going? Something helpful.
Did you cross out 1? Did you cross out?
Okay, I'm hearing 2 things. One of them is the right direction, and one of them is the most commonly taken direction. Sadly, they're not the same thing. But that's okay. Let's figure out why I have these things up on my wall. Someone keeps turning that too. I heard cross out, and I heard multiply. One is right, and one is the most commonly taken. Which one do you guys think is the most commonly taken? Cross out.
Dang.
But guess what dies?
Kill the kitten.
I don't like cats.
Do you guys read what this rule
I
is?
don't like cats. I don't like gone.
Some people might think that they can't really see it because of the smart board, so let me help out real fast. Up on the wall, I have, every time you do this, a kitten dies, and here's the actual example I have. I have x squared plus 2x minus 15 all over x squared minus 4. And some poor little math student somewhere said, yay!
No.
But it's the most commonly taken, including on your 5.1, 5.2 quiz that we took last week. This mistake was made again and again and again because, look at this example. Don't some of you really want to say, yay?
Yeah, that'd be great.
But you're wrong, and a kitten died, and here's why, okay? What's the proper way of doing that problem? Factor.
Oh, jeez.
You cannot reduce unless they match top and bottom. And right now I have a trinomial and a binomial that are very different. But if I was able to factor, then I'll be able to see, can anything really reduce?
No.
There's nothing in common. You're like, well, there are x's. Yeah, but there's not an x minus 3 or an x plus 5 or an x plus 2. No, some of you think that way. That's okay. We just need to change your brain to realizing another kitten still died. And another one still died. And that doesn't even make sense. What's left?
Okay, this whole page.
There's that kid blood on my hand.
No, seriously. For their Calc AB sweatshirt, no, Calc BC, Corey Shower wanted to make like a whole field of dead little puppies, and the girl saying, one survived. Anyway, so. It was actually really cute, though, because they're like these cute little puppies that they're sleeping each other.
But they're dead.
But it was horrible. So we got the NASA one. I'm not going to go around there. So what's the legal? That's why we didn't make it. Got the NASA one. How do you solve? I said multiply. Chris said multiply. I stole it.
Oh, Chris.
How? Okay, other Chris. But how do we multiply? What do we multiply? Dang.
Yeah.
That's legal if we do it to one side and to the other. That's legal. The other one was not. What do we have left? What, 0 times anybody? 0. That is doable. Alright, let's solve this puppy. Here we go. It's an alive puppy, keep it that way. Okay, so. Guys, math, come on, math. Just get X alone. Oh, don't get X alone, get the trig alone, then we'll figure out that. What do you say, Mike?
You could subtract by 1.
Good, subtract the 1, and can we see the next step? I mean, we're in 3 now. Subtract the 1, then divide by 2. Algebra would say subtract first, then divide. So I get -1/2. Okay, cool, now what?
Square root.
Square root. So I have absolute value of sign, which leads me eventually to a plus minus. I'm just having fun doing what I'm supposed to be doing. And now it's time for me to actually figure out this happens when. AJ's doing good. If it was a positive 1/2, you would have 1 over root 2, which is root 2 over 2, which would be a 45. But the problem is, it's not a positive 1/2.
It's negative.
Isn't that, because it's negative, it is imaginary. So, if it's imaginary, are we looking for imaginary answers in between 0 and 2 pi?
No.
What are we going to say?
It doesn't work.
Good try trying to trick me, but this is not
solution.
possible. There is no solution.
Wait, so all that work is nothing?
Yeah, all that work for a right answer.
What do you have it right? That's plus 3. But there's nothing you can do. Like,
Come on now.
What is the purpose of that?
Yes.
That
was plus 3 times 2.
I think you have a whole. I think you have a whole profession that would be a bit disappointed to hear you say that no solution is a waste of time.
Oh.
Aren't there a lot of people out there doing a lot of research for a lot of solutions, a lot of different ways? And if they get an impossible, isn't that a chance for them to say, okay, let's forget this hole and let's pursue this whole direction instead? A lot of people in a lot of different labs would say no solution is at least a clear stop that, start this, okay, poof, I can forget all of that. It's a good thing, not a bad thing. Here we go.
No solution is self.
Exactly, nicely done. How about this one? Let's just do 0 to 2 pi again. There's not even a cosecant. Stop bellyaching. What should we do?
Do something.
Yeah, I like that. I like that. Why not just add this in? That's a good idea. But wait, it just got real weird up in here. There's that whole thing deal to people that if someone told them no solution without actually proving it, man, cure for cancer and they just said no solution, that's a bummer. Okay, how do we, we transform sine to be 1 over cosine. If only we can make the sine into cosine and cosine into sine.
We
Equals cotangent.
Oh, divide? We could divide.
If you divide by
Well, if we divide by sine, I think that might be cotangent. You want to divide by cosine?
Sure. Oh, you're right.
When we divide, that doesn't equal 0, that equals
1.
yeah.
Are you okay, Michael?
So who's sine over cosine?
Tangent.
So sine equals cosine when tangent equals 1. Some of you who really know your unit circle might have gotten here before us. When is sine and cosine the same? When is the x and the y the same? When is the over and the up the same? When is the
45.
Is that also when tangent equals 1?
Yes, ma'am. Yeah.
Ah, this is going to happen at 45. Oh wait, all quadrants? Wait. Not all quadrants. Because is it sometimes, don't their signs sometimes disagree?
Yes.
We need their signs to agree. We need them to be exactly the same. We need tangent to be a positive one. So in what quadrants will tangent be a positive?
1 and 3.
All
1 and 3.
and tangent. Good. So just need to make the connection. A 45 is what kind of radian?
Power 4.
Yeah, cut the cows down into fours. 1, 2, 3, 4. So that's going to be pi over 4.
5 pi over 4.
And all 4 and one more. 5 pi. Keep going? No, just 0 to 2 pi. We can't keep going around, or else we're going to be too big. So therefore, dun 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 dun. Dun dun. You're welcome. Making it memorable. Between Bumblebee and standing up and me knocking the sidewalk. Guys, do we have to be creative from time to time?
Yes.
Is the unit circle important?
Yes.
Is it supposed to be impossible?
Yes.
Joe, what's up, bud?
Negative.
Yeah, 0 to 2 pi is 1 pi and then 2 pi. So we're only allowed to go positive because it was 0 to, not the negative side. And then if we did try to keep going, we'd have to pass 2 pi and we'd be going towards 3 pi. Or just think that's 0 to 360, so only 1 time around. Alright. Ooh! Let's do, we haven't done a new direction in a while. Let's just do all solutions. Let's just do all. Limitless but limited. Infinitely many. Number 38 is a homework problem? I don't think they're all in homework exercises. I try not to do necessarily all ones, but every now and then I do one, don't I? You guys have caught me on that before, and I'm like, you did it yesterday. Guys, help me out though. Secant plus tangent. That's not quite like easy, it's 45. No, it's a little harder. What do you want to change?
Oh, wait. Secant is 1 plus.
Okay, hold on, pause. Chris thought of something good. There is a formula with tangent and secant and a 1, but that's Pythagorean and they all have to be,
I know it's just
Can we swear?
turn the secant into 1 over cosine, and then the tangent into sine over cosine.
So guys, even though there are Pythagoreans that sometimes help secant and tangent go together, you need squares. So don't get stuck on, you always have to make the secant and the, just, if worst comes to worst, take a step back and say, whatever, change them all to sines and cosines, because you can always do that. So Lainey was like, well, let's just make it 1 over cosine. Jacob, what's that then?
But if you square everything, isn't it still equal?
Dilemma.
Both sides.
Dilemma. You're right. We are allowed to do this, but pause. If I were you, don't write it down. Don't kill a puppy. If we were to square this, it wouldn't be secant squared plus tangent squared. It'd be secant squared, outer and inner times 2, plus 2 secant x, you have to FOIL it. These are squares, but he's not. And so it's a good idea, but we're still not quite there. Does that make sense?
Where does it?
It's like.
You have to write it next to each other, and do the first, and the outer, and the inner, and the left. Capture the bubble bees helping right now. Okay, so,
Pause. Why is this helpful? Do you need one, or do you already have a common denominator? 1 plus sine all over cosine equals 1. Hopefully none of you would go canceling anyways. It doesn't even look like you could, even though you can't. But what are you going to do anyway? Multiply. So 1 plus sine equals cosine. Oh, I apologize. I was multiplying. That was hard. The air randomly turned on, but at this point we literally have 45 seconds. Then I'll go change it for next period. What do you do? 1 plus sine equals cosine. I can't divide. I can't subtract. Jacob, what did you say you could do to both sides? But if I legally square, everything's not better. But question, what can I make cosine squared?
One minus.
Can I move it to the other side and maybe have a quadratic that I could try to factor?
Yes.
I ended on a hard one so I could give you Alright, okay, it's homework. Work on it for tomorrow. Have your notes close. Have your unit circle close. Use the examples to give you ideas. Questions tomorrow. Always Bible studies. Bye guys.